of Kepler's labyrinth. And the first one is we are given delta t, the time of flight, equal to 5 tu, and p equal to 5 du, and e equal to 1. So we are given the type of the orbit, 2 orbital elements, we can determine everything. And we're going to find the eccentric anomaly, because this is for parabolic. And in terms of our orbit, we're using B as an eccentric anomaly for parabolic orbits. So right now, with this kind of the handy formula sheets ready, so we know the M by looking into our things is B cubed 3 plus B. And n actually relating to 2 and delta t. Okay, so that is from our equations here. And we're going to solve for B. So right now you can see we are given the left-hand side information. So therefore from here the 2 times 1, 5 cube multiplied with 5 and equal to b cubed over 3 plus b. And this one, we can solve for this one either numerically. This one is how much? Two times this one, I think. Okay. So solve for b, and you should be able to get it at b equal to 3.8174 and in radian. We have equations for a closed form solution for this kind of polynomial. And on the other side, if you're going to use MATLAB, and in MATLAB, and you can try this. Basically, for this one, you can write into this word is 3 plus b minus 2 1/5 equal to 0. So simply in MATLAB, you're simply using roots and arranging the coefficients of polynomial functions in descending orders. So 1, 3, and the second one, b squared is 0, and b equal to 1, b to the 0 power is 2 times this one. You put this one in an array, and array is put into the angles bracket, and you put in this one, the MATLAB will give you the numbers as well. Okay, but otherwise this one we can calculate using the formula. I think the formula available on our handouts here. So this is the easy problems of the Kepler's, and we look at the second one. Second one is a little bit challenging. This one needs a little bit calculations. Okay, so basically here we are given the initial positions and velocity, and we also know the time of flight in terms of the data nu. So we want to determine the final positions and the final velocity given this kind of such things. So given this, we need to determine what kind of orbit this will be. So this one will involve the determine the orbital elements, and so that will be go to the very beginning of our these chapters. So from there, the first step is to determine using as long as we know the position and velocity at any time moment, we can right away to determine the orbit. And here, let me skip up the details, and that one, let me give is P equal to 8, and A equal to minus . Okay, so that is this orbit. This is a hyperbolic orbit. And now we know the starting point, and we know the time of flight relating to this one. We want to determine the final positions. So here, this is a hyperbolic. So the concept is this. For hyperbolic, this equation, let me write down the equation we need. And m minus m0 will be equal to E hypersine f minus f minus E hypersine f0 minus f0. Okay, and what is m0? M0 basically is the n. What is n? I don't have n. Okay, so that is the equations I pick it up from our handouts here. So now we can see. First one, we know the initial conditions. We can determine the mu0. So from here, we also determine the mu0 equal to 0 degrees. So that makes things easier. So now we can see, we know the initial, so we can determine the f0 here. Okay? So hypertangent f over 2 equal to E minus E. Because the nu is equal to 0, so therefore okay, so using the initial true anomaly, we can determine this one. And so this term is gone. And now we are given is data nu, so therefore the nu So this is for our initial conditions. And now we traveling by that much to anomaly angle, so therefore in at the destinations, I would say this is our destinations, okay? So let me say the nu equal to nu 0 plus theta nu, and that is 60 degrees. Okay, so that's the first piece. The second piece, informations. So from here we determine nu, we can also determine the f, so therefore f will be equal to, f is the corresponding eccentric anomaly corresponding to this traveling period. Okay, so from here we can determine f, and that one will be equal to 1.0053, and that everything come up is in radian. Be good. So from here we can determine the traveling time. So on this side we have on the right hand side we have everything determined already. So therefore from these equations we know the t minus t0, that is our delta t, the time of flight. Plug in this equation, again, the right-hand side is a number we have fixed. So we can calculate, determine t, and the t time of flight equal to 1.0835 TU. And we want to determine this one, and R, and how to do this one. If you remember one equation, that equation is on the cheat sheet. In PQW, in the perifocal corner systems, we have the R formula that is on the cheat sheet. And that one is equal to R cosine mu, R sine mu 0. Again, I want to emphasize is in the PQW systems. And what is R? R is the distance, and we can use our orbital equations, P and 1 plus E times cosine nu. And right now, because at that moment we calculated nu equal to 60 degrees, so therefore from here the P is from our orbital element determinations, and nu is from the calculation here. So we can calculate R equal to 2.4035 EU. So from here we can determine R, and PQW, that will be equal to 1.2018, 2.050. Again, this is in PQW. Okay, that is in the unit DU. And velocity in perifocal corner systems, and the formula is mu over P minus sine. Okay, so that one implemented will be equal to okay, so right now from here we have calculated the positions and velocity in terms of the perifocal systems. But here we want to determine those expressions in terms of the IJK corner systems. Okay, and since right now this one we calculate time of flight doesn't use in our remaining calculation, but that's okay. Okay, so now with these things and how to determine, again on the cheat sheet, R, IJK, and that is a big calculations. Then you write it down by equations again, and that one is equal to, let me put into T matrix, okay. T is equal to this one, cosine omega minus sine omega. Multiply with this equation is on the cheat sheet, and these tell us the transformation between the parafocal system to geocentric coordinate systems. And omega, capital omega, is the angle between the I-axis to the line of notes. The I is the inclinations of the orbital plane. The smaller omega, that is the angle from line of notes to eccentricity factors there. Okay, so basically those are the part of the orbital elements will be previously calculated. So simply plug into here, then this one will be equal to okay? So the two are our final answers. For these questions, and being honest with you, last week when I reviewed my lecture notes, and my lecture notes only stop at here. And my lecture notes stop at here, so I kind of keep thinking, am I be able to further express this one into the IJK? So kind of looking at the old stuff, and then, oh, here we have this kind of the transformations. So I simply plug in. And in this way, again, I write simple programs in MATLAB to tell the transformation between IJK, between the IJK and P to W. Okay. So that is the whole calculation for this one. And this one involves quite a bit different pieces of the concept among these chapters. So I think this will be the good one. And on the calculation side, this involves quite a bit of calculations. So just for your reference. After our second test, and we will be still on the Kepler's problem, we will go into the second portions of the Kepler's problems. In that second portion, we're going to introduce a different approach. In that approach, solving this problem will become easy. And so that is our second note. And you might ask me, why not you directly show us the easy approach rather than show us the hard one? Because the reason is those kind of concept is will make the explanation of the Kepler's problems easier because we piece by piece dealing with the detailed calculation per orbital type. The second portion is universal approach. They simply merge all the type of the calculation into a single one. So in terms of the concept, that is a little bit challenging. So that's the arrangement for this. Okay, so that is for this one, and